In this lecture, I want to present the equations for the different types of energy that we'll be using in this chapter. We're not going to have an equation for every single type of energy, but these are the equations for the mechanical forms of energy and thermal energy that we'll be covering in this chapter. So we have kinetic energy, which I've previously introduced as energy of motion. Kinetic energy depends both on the mass and the velocity of the object. It turns out to be 1/2 mv squared. Notice that since v is squared, the direction doesn't matter. So it really depends on the speed. So even though we use v in the equation, it's the speed really that goes in there, since squaring it gets rid of any directional information that we might have. And kinetic energy is not a vector. Energy in general is not a vector. Now, something that's spinning has kinetic energy too. How much? Well, it depends on its moment of inertia and its angular velocity. Notice how analogous these are, right? Inertia for straight line motion is its mass. For rotational motion, it is moment of inertia. This is your straight line speed. This is your angular speed. Potential energy. Remember, potential energy is energy of position. It does not necessarily mean something's about to happen. It is energy of position. And so in this chapter, we're going to talk about two different types of potential energy. We're going to talk about gravitational potential energy, which depends on the height of an object. That is mgy. I've included this note here. We assume that the potential energy is 0 when y equals 0. Well, what does that mean? This is sort of a subtle point, but potential energy is we only care about changes in potential energy, really, right? In other words, in the previous segment, I talked a lot about the potential energy of this ball sitting on this box. And yeah, I don't think anyone was too blown away by saying, hey, it's got potential energy because it's on the box. Well, how much? Well, now I've got an equation, mgy. Well, what should I plug in for these? Well, what's m? That's the mass of the baseball. 180 grams, something like that. G, 9.8, right? That's 9.8 meters per second squared. Y. Y is the height from where? From wherever I'm calling potential energy equals 0, right? So this box is sitting on my desk. It's about, it's not that big. I don't know. It's what, half a meter. Let's call that half a meter. It's half a meter high, right? So is the potential energy of this ball m times g times half a meter? Well, the thing is, though, is that my box is sitting on my desk, and my desk is 1 meter above the ground. And so it turns out that this ball is actually 1.5 meters above the ground. So maybe its potential energy should be m times g times 1.5 meters. But I'm in the basement. I'm actually about 2 meters below my kitchen right now. So maybe it has negative potential energy because I'm below the main floor of my house. Which one is right? The answer is they're all right. We really only care about changes in potential energy. And so, we just say, hey, let's make gravitational potential energy equal 0 at the lowest point in our problem, and that'll make everything work out. So in this, it does kind of make sense to have the floor of my basement as 0 of potential energy, because, it's where my ball's going to end up if I drop it. But it kind of doesn't matter, right? It's got an enormous amount of potential energy compared to, say, Death Valley, just because I'm in Fort Collins, which is at 5,000 feet above sea level. So what's the right answer for where 0 is? My floor upstairs, my floor in my basement, my tabletop, Death Valley, they're all right. We just have to decide and be consistent. All right, spring potential energy. I can store energy in a spring if I compress it or I stretch it. How much? Well, it depends on the spring constant and how much I've stretched or compressed it. Recall that delta x is the change in the length of the spring. So 1/2 k delta x squared is spring potential energy. Again, they're both potential energy because they are energy of position. Lastly, thermal energy. Thermal energy is related to the microscopic motion of the molecules of a substance in a way that we'll talk more about in chapter 12. So you can heat up your hands by rubbing them back and forth, right? And so in this case, I'm doing work, forces, right? Forces over a distance, through a distance. I'm doing work to create some energy, to add some energy to the system, I should say. What kind of energy? Thermal energy. I can feel my hands getting warmed. It turns out that temperature is a measure of the average kinetic energy of the molecules that make up a substance. So when I rub my hands together like this, then friction is causing the molecules in my hands to vibrate faster. They warm up. I have added thermal energy to my hands. So friction is the way we create thermal energy. Again, until we talk about heat. So thermal energy involves friction. And so force times distance, well, that's work. So we can think about this as the work done by friction. Well, when friction does work on something, it removes energy from the system and it creates thermal energy.